Okay guys, so in the previous lectures we were seeing the series or consecutive reactions, and we saw the concentration of C at any particular point of time. So we'll be continuing from that. So we actually wrote A naught was equals to concentration of A at any point of time T plus concentration of B at any point of time T and concentration of C at time T. And we also wrote that dA by dt, the concentration of A by dt, would be equals to K1 times A1, rather A1 times A only, and minus dB by dt was equals to K1 times A minus K2 times B, and minus dC by dt would be equals to K2 times concentration of B. Okay, so the following graphs can be drawn for the same. So we have concentration on y-axis and time on x-axis. So this is assuming that K1 is greater than K2. Then we can draw this graph for A, or the concentration of A, and we can draw this graph for B, and can have this graph for C. Okay, then if we see what will be the nature of graph when K1 is greater than equals to, rather greater than K2. So in this case what we'll have is, again, this would be the nature of concentration of A, rather let me make it more finer. This would be concentration of A, then this would be the graph for concentration of B, and finally this would be the graph for concentration of C. Okay, so now let's see what will happen if K2 is greater than K1. So in this case we can have that this is again concentration with time. So for A definitely we would have something, so this is like this. Okay, similarly you can draw the arrows for the respective graphs as well. Okay, so in this case, as K2 is greater than K1, so concentration of A would be dropping drastically, and for B also it won't be having such a high peak, it would be a small peak, something like this. But the concentration of C would be skyrocketing. Why? Because K2 is greater than K1, hence we'll have something like this as the graph. Next, let us see another important concept, which is Arrhenius equations. Arrhenius equations. Okay, this is ARR. So K can be written as A times e to the power minus EA upon RT. This is the Arrhenius equation, where K is obviously the rate constant, and A and EA are Arrhenius parameters. Okay, and A can also be written as pre-exponential factor or frequency factor. or frequency factor, and EA can be written as R activation energy which can be measured in terms of joule per mole. Okay, and one more point to note here, that if T is infinite or activation energy is 0, then we can write that the rate constant is equals to the frequency factor or pre-exponential factor. Okay, and also to note that A and K have same units or unit whatever. Okay, so for any general irreversible reaction we can write that, so we have K equals to A e to the power minus E upon RT. So taking ln both the sides, we would have ln K equals to ln A minus E upon RT. This is E A subscript. Okay, so the graph would be looking something like, if we draw the graph of ln of rate constant upon and 1 by t, so it would be looking like this, where slope is minus EA upon RT and this intercept is ln A. Okay, and T1 is, this is 1 upon T. 1 upon T is temperature. So at, let's say we have T1 and T2 points, so T1 would be, so we have a pair T1 comma K1, so K1 would be rate constant at temperature T1, and similarly T2 would be rather K2 would be rate constant at temperature T2. Okay, and we are also taking some assumption that EA and A throughout the course of the reaction remains constant, which are the Arrhenius parameters remains constant, or also we can say that they have no appreciable change. During the course of reaction. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing more on the Arrhenius equation for general irreversible reaction. Till then, good luck and goodbye.